Here.
It's my pleasure to introduce Anurag Rao, the Technion, talk about dynamical questions from the theorem.
Yeah, so thanks to Noy, Iran, Uri, all the organizers of the seminar. Okay, so yeah, I am going to talk about Dirichlet's theorem and how it's inspiring me to do research in homogeneous dynamics. So if I have to state a theorem, I'll be done with one slide. So I have to talk about something else. So let me talk about motivation or more survey-like things. Okay. Okay, so this is Dirichlet's theorem. So you're given a real number, alpha, and you look at q times alpha. You want to see how close you get to z. To get within 1 over t of z, you just need to go less than t steps. That's what Dirichlet's theorem says. So for any alpha and for any large t, we can solve the system in P and Q. So, okay, so why do I say this is Dirichlet's theorem? Of course, I can change this 1 to 1.5 or something. The theorem still holds, but why is this 1 optimal? So that was studied by Davenport-Schmidt. There any way I can see like one slide at a time? Or
full screen. Yeah.
Yes, in full screen, I think. Maybe you can move the sidebar along. If you can close the sidebar, that could help.
Okay, okay. Okay, maybe it's fine. Okay. So, okay, so this thing about improving Dirichlet's theorem was started by Davenport-Schmidt in 1969, this very famous paper. They proved this theorem that if you take some constant less than 1, then for Lebesgue almost no real number can you solve this system for all large enough t. And then this is the sense in which the constant 1 is optimal. So they gave this definition of the set of Dirichlet-improvable real numbers written Di. And it's just the set of numbers for which this system, the Dirichlet system with C, with this, it's the set of numbers for which there exists some C less than 1, for which this system can be solved for all sufficiently large t. Okay, so I hope the definition is clear. So they proved it's measure 0, but it's not empty. It's very large. It has full Hausdorff dimension. Okay, and the way the real content is that it's large. It has Hausdorff dimension 1. So the way they proved this was that they gave a perfect characterization of the set.
What is Di?
The set of all real numbers such that there is some C less than 1, such that this system is solvable. Yeah, lot of quantifiers. I'm sorry.
So when you prove the theorem, it's trivial proof, right?
I mean, the natural thing is just use pigeonhole principle, right?
And the pigeonhole principle, you take the rationals and you cover them with intervals, right?
Pigeonhole is just you divide the unit interval into
subintervals of length
about 1 over t, and then you count
so
0 alpha.
Now the point is that it will be like maybe 0.3 over t, c 0.3, and then those intervals will not cover.
Yeah.
That's where the 1 comes from. I'm just making sure I understand.
Sure, maybe the 1 comes from somewhere else. We'll see. Yeah, that's a good question. Okay. Okay. So I hope Di is an important set. I hope the definition is clear. So what they did was they characterized Di completely. The number is in Di if and only if the continued fraction expansion either terminates, either it's rational or it has bounded digits. And the latter set, the set of numbers with bounded digit continued fraction is called the set of badly approximable real numbers. And it's defined to be the set of real numbers alpha, for which this system, alpha q minus p, less than c over q, has only finitely many solutions. So you can't get two good approximations, alpha minus p over q, in terms of 1 over q squared. You can't get arbitrary constants close to 0. Okay, so that's the set BA. And then prior to this paper, Schmidt had already written this seminal paper about Schmidt games, where he had proved that BA is a very large set. He proved that it has full Hausdorff dimension, which was an old result going back to Yarnik, but he proved something stronger, that it's winning for a certain game. So, I mean, okay, maybe because this is...
DI and BA, how do they relate?
Here, DI is exactly, so DI, they prove that DI is equal to Q union DA. So this is what they proved. And then, yes, some work went into giving this characterization, and that was what it was in the paper. And prior to that, Schmidt had proved that this set is large. So then they wrote it as, I guess, a theorem that DI has full dimension, or DI is one. Okay, so yeah, briefly, Schmidt games are like super important. People here work on them all the time. What it is, it's a game played on a complete metric space. So you have XD, a complete metric space, and a subset S. And you have two parameters, alpha, beta, between 0 and 1, and two players, Alice and Bob, who play the game in turns. It's a turn-based game. Okay, so Bob chooses any ball, base 0. Do people see this?
No,
No?
those on the Zoom probably cannot.
Okay, so
But we can.
you can, yeah, okay. So this is X, and you have some subset S, and then you start with the 0, that's what Bob chooses, and then Alice chooses another ball of A1, which has radius alpha times the radius of B0, and they keep trading with the same ratios of previous radii. Okay, so if the intersection is in S, then Alice wins, and otherwise Bob wins, Alice loses. So a set S is said to be winning if there is some alpha, some parameter alpha, such that for all beta, Alice has an alpha beta winning strategy for every beta greater than 0. Okay, so consequences of this, of producing winning strategies are that, okay, any winning set has full Hausdorff dimension. So Schmidt gave a winning strategy for BA with alpha less than half. So in particular, BA has full Hausdorff dimension. More properties of winning sets, which are, they're closed under finite intersections. If you have the same alpha, then countable, but if you have different alpha, then that's why it's okay. The winning sets are also preserved under Lipschitz maps. And yeah, this is, so Davenport-Schmidt used this Schmidt result, and then they said, okay, DI is a non-empty set, it's a non-trivial set. Okay, and in that paper, or maybe a paper after that, they showed a similar kind of, they made a similar kind of Dirichlet-improvable study for Dirichlet's theorem, a higher dimensional version of Dirichlet's theorem, where they were looking at approximation of one linear form or even simultaneous approximation. So there, of course, they didn't have a perfect characterization of the set DI, but they still proved that BA is a subset of DI. They wrote down some argument, some element-wise argument, and they got the same result. DI measures 0, but it's large. Okay, so I want to highlight some of the dynamics that's going on here. So to do that, I'm going to, let's prove another Dirichlet theorem. Okay, so instead of talking about real numbers, let's talk about complex numbers. So here, the setup is that alpha belongs to C. P and Q are now Eisenstein integers. So, I don't know. Okay, so I need to fix this J. What is this J? Okay, so this is the complex plane. This is 1, this is I. This is J, which is the third root of unity over here. You have another one here, this one. Okay. And then Zj is just the ring of Eisenstein integers. So it's generated by 1J, so you get a whole bunch of points. It's a lattice what you get. Yeah, it's like Z and R. You have Zj and Z. And
This is a quadratic extension of P, right? It's a
yeah, minus 1/2 plus I squared root 3 over 2. Yeah. You take the field of fractions, it still bends. So you can talk about Diophantine approximation. Okay. Okay. So say we want to prove a Dirichlet theorem. Say I want to find an optimal constant C such that this system can be solved for all PQ. So this system can be solved for all P sufficiently large in PQ belonging to Zj. Is it clear? So yeah, now it's weird. This pigeonhole is like, again, kind of weird here. Okay, so how do we do this? Well, one way is to just look at this condition 4. It's actually asking about a set theoretic intersection. So this condition 4 can be rewritten as whether or not, or it can be rewritten as the statement that this lattice intersected with this set in C2 is not 0.
What is lambda alpha j?
So lambda alpha j is it's a subset of C2. So it's exactly So it's exactly 1 alpha 0 1, the set of 1 alpha 0 1 times PQ, where PQ belong to Zj. So the typical point exactly looks like what showed up here. I guess, yeah. Or yeah, Q alpha plus P. I guess I want the minus, then Q. It's a set of all these things. Okay, and P infinity 1, there's some abuse of notation here, but it's the soup norm ball in C2. So it's a set of all tuples of complex numbers, VW, such that the maximum of absolute value Z, absolute value W is less than 1. Okay, so I hope this is absolutely clear. This saying there is a solution for this system is nothing but this set theoretic intersection being non-empty. Sort of like crucial.
So you took a box in C times C and thinking of R times R.
Yes.
And you kind of skewed it in a diagonal way where you
this
changed one dimension to C over T and the other dimension to T.
exactly. So here I have 2 copies of C, and then the X coordinate is shrinking and the Y coordinate is increasing. And it's not like, this matrix is not determinant 1, it's slightly off. But the whole point is that, okay, I guess the whole point is that you can make it determinant 1. Okay, so
you converted the problem to saying I have a certain family of lattices in C times C.
yeah, yes.
These are honest, discrete, finite covolume subgroups of C times C.
Yeah.
And you have these boxes, and you want all these lattices to contain a non-zero lattice point in all these boxes.
Yeah.
So it's very reminiscent of what's his name?
Yeah. exactly. So yeah, I guess okay. So why are we normalizing here? Okay, no, we're normalizing. Yeah, bear with me. We're going to normalize now. I want to. This is not. I mean, this is like a. Yeah, I don't like it. Okay. So what I'm going to do is I'm going to define f to be ln p over square root c, and then I'm going to apply an automorphism of C2 to this equation. So if this is not empty, then certainly this is also not empty, and conversely. So that's equivalent to this. Okay, so what I've done is that I've sort of changed the motion to the lattice, and then the ball is staying constant. So now we're dealing with an honest to God, just one soup norm ball in P2. Okay. And this thing I'm going to write GS. So it's a diagonal, one parameter, non-compact diagonal. It's just this, e to the s, e to the minus s, as a real number. Okay. Questions? Okay.
Maybe the question I have in mind is lattice lambda alpha j. What's its covolume?
I mean,
C square. Because
you look z. Zj you can write a basis as 1, 0, 1 over 2 square root 3 over 2. So when you take the product, it turns out to be 3 over 2. So it's not determinant. It's not covolume 1. I mean, look at Zj inside C2. Yeah, and
regardless of alpha, it's always
3 over 4. Yeah, maybe that's good to keep in mind. I mean, yeah,
it's a constant. It will pop up.
Yeah, we'll use it. Yeah, exactly. Okay, so I hope what Minkowski's convex body theorem says is that if you're in Rn and you have a symmetric convex body of volume greater than 2 to the n, then you have to intersect the standard lattice Zn non-trivially. You can do some change of variables and then see that what it says in this case is that if the volume, the infinity C, is greater than 16 times the covolume of this, then the intersection, this guy, will always be non-empty. So we can always solve Dirichlet's theorem for that constant. So the constant you get, so we can do a quick computation. What is the volume of B infinity square root C? So it's pi r squared. Yeah, so it's pi c squared. And then the right side is 16 times the co-volume. As we saw, 3 over 4, you get 12, yeah. So you want this C to be greater than something like 1.1, and then you have a Dirichlet theorem. Wow, okay. but is it optimal? No. So the precise Dirichlet theorem is this. So the right constant is 1. Okay.
Wait, so this was 1.1, and now you're saying that you can.
No, yeah, it's 1. It's 1.
But this one, the one that we computed was 1.1 roughly.
Yeah.
And you can improve it for some reason.
Yeah. There's some wastage. Yeah. Again, we won't do any work. We will stand on the shoulders of Minkowski again. Okay. Okay, so we're going to put together this new Dirichlet theorem without doing any work. Okay? And it's as good as Davenport-Schmidt's theorem. So yeah, maybe I can make a career out of this. Okay, so this is theorem. For every complex number, this system can be solved for all sufficiently large T. Of course, we're looking for solutions P and Q and Zj. There's no square here. Yeah, just P, Q, or yeah, either that. Yeah. Okay, and we can again define this Dirichlet-improvable set I'm going to call it Dij this time. It's a set of all complex numbers such that for some c less than 1, I can solve this system with c over here. Alpha q minus p absolute value less than c over d. And again, q goes from 0 to p. So it can be solved for all sufficiently large c. Then again, Dij has Lebesgue measure 0, but it contains Daj, and so has full Hausdorff dimension. In fact, it's winning. Okay, and Daj is defined analogously. It's the set of all complex numbers alpha such that this alpha q minus p greater than c over q cannot be improved. I mean, there's some constant c such that the equation alpha q minus p less than c over q has only finitely many solutions. Exactly like the real case. Okay. So let's see how to put this together. Okay. So
will you show us that, or will you explain why one is the?
yes, absolutely. Yeah. Okay. So I guess the brilliant insight of maybe like Kleinbach is that Dirichlet's theorem is saying something about this intersection being non-empty for all of these alphas. Okay, and yeah, I can remind you again. So lambda alpha j is 1 alpha 0 1 zj squared. This is the geodesic thing. So if you forget about this subset of lattices and just think about a bigger set of lattices, which is xj going to be SL2C mod SL2ZJ, identified with actual subsets of C2 by m going to m times Zj squared. Maybe think about the constant that works for this entire space. Right? So that'll definitely do the trick. But maybe there is wastage, maybe not. So let's define that constant. So let's call it the critical radius. Rj is the supremum of all real numbers such that this has 0 intersection for some lattice in the larger space.
This xj, if I understand correctly, it has nothing to do with j. It's the space of lattices in C times C, which are direct sum of
I mean, they have 2 independent C vectors, but I mean, it's not like the Zi is not in this. I mean,
It's just a way of parameterizing the set of lattices in C square.
it's one, yeah.
but I'm afraid that I am not understanding. There is I interpreted a contradiction. So what is this? This is the moduli space for some space of lattices. Which lattices?
I use it. So discrete Zj submodules of C2, of which can be represented by a determinant 1 matrix. Full discrete, full rank 2 submodules.
It has everything to do with J.
Yes.
Only Zj module.
Yes. Everything to do with Zj. Okay. Yeah. So I mean, this confuses me as well. Okay. So Rj is the largest number we can find, such that there's one of these lattices which intersects the B infinity R ball trivially. So again, okay, Minkowski's convex body theorem tells you that this is actually finite. Rj is actually finite. So it's some number. Of course, okay. So it exists. Okay. Now, yeah, clearly if C is greater than Rj squared, then this system, you can go back and say that this system can be solved for all sufficiently large t, of course. Just by definition of Rj. Okay. Yeah, so it turns out that this Rj is actually Rj squared is actually optimal. in Dirichlet's theorem. So I haven't showed you that Rj is 1 or something, but I'm just abstractly telling you that there is this constant which is optimal for Dirichlet's theorem.
So it's optimal by definition, right?
I mean, you still have to show that if you go a little lower, then you get a measure 0 set in that sense.
Oh, you mean it's optimal for Dirichlet?
For Dirichlet, yeah.
Yeah.
So the optimality comes in Davenport-Schmidt's definition, where if you go a little lower, you suddenly get a 0 measure set. We should still have to show that.
Zero measure or 0 dimension?
0 measure. Okay, we'll go through it. We'll go through it. Yeah. Okay, so now that we have this Rj, this finite constant.
So Rj, I can think of it as the optimal R for which Minkowski's convex body theorem will hold for these lattices.
Why are you saying Minkowski's
xj? And you're saying
yeah. For this specific body, maybe.
Subspace of 4 dimensions. Not all of them, and maybe
for this
better
subspace.
radius than the radius given by Minkowski.
So it also depends on this thing actually. Like this is a disk time disk.
It's a particular norm.
Yeah.
It's not a general convex symmetry.
Yeah. Specific to this one. So now that we have this Rj, let's define this critical locus, which is a subset of the set of Eisenstein lattices, xj. It's the set of lattices which actually intersect Drj trivially. Okay, so why is this non-empty? So we know that if Rn is a sequence that increases to Rj,
The optimality comes from the ergodicity of the.
Yeah, exactly. Yeah. It's very straightforward. Yeah. So, okay, so let me just say, why is the critical locus non-empty? It follows from some compactness argument of Mahler. So basically, if Rn increases to Rj, for each of these n's, you get a lambda n, for which the intersection is trivial. And then this Mahler argument just says you have a convergent subsequence, this lambda n. So that gives you a point here. So it's not empty. It's again compact by this Mahler argument. And a system of neighborhoods is given by this family. So you look at all R going from 0 to Rj. These LJR are the set of lattices, Eisenstein lattices, which intersect this smaller ball trivially. So there's
maybe one comment that if maybe you all can enjoy it. This space xj, it sits inside SL4R mod SL4D, and it's the closed orbit of a subgroup of SL4 who the standard that is Z4. So Z4 is identified with, like in my head, it's identified with this
Eisenstein. Yeah.
And this SL2C it has a representation in SL4, and the modular space you consider is just a closed orbit of that subgroup of SL4. So you're doing what we do all the time somehow, but in a subspace of SL4R.
Yes. Right. Okay. So we have this system of compact neighborhoods. The point I want to make here is that these guys are open. So if you look at the Haar measure, each of these things gets positive mass. Yeah. Okay. I mean, they're compact neighborhoods, so they get positive. They're not open. Sorry. Okay. So as Uli said, ergodicity is going to show the optimality of this constant. Okay. So the diagonal action is ergodic on xj. And that, along with maybe a standard Houdini argument of decomposing xj along two directions shows that, so using ergodicity and the fact that somehow this subspace of lattices controls what happens in the bigger space, you can see that for almost every complex number, once you embed it in the lattice, the space of lattices, you can find a sequence of unbounded times Sn and something in the critical locus such that Gsn lambda alpha j converges to lambda. This is just by ergodicity.
Even by density of almost any.
Yeah, just the fact, exactly. Yeah, just, yeah. Yeah. So, like, let's try and see how that implies that this Rj is the optimal constant. So that means for any c less than Rj squared, that means square root c less than Rj, for almost every alpha, you can find a sequence of times such that Gsn sends lambda alpha j into, I guess, one of these neighborhoods. That's where ergodicity is coming from. So that means you have zero intersection with this form. Again, unwinding and making this change of variables shows that this has no solution for all those times. Okay, so it's a very standard argument if you think about it. Are there any questions? Okay. Yeah, so incidentally, what we've shown is some kind of correspondence. So we've shown that there is an optimal constant Rj, and we've shown that almost no alpha is directly improvable. And we have this equivalence, which says that a number is directly improvable if and only if it eventually avoids a neighborhood of the critical locus. Again, I didn't say this explicitly, but it's just a change of variables. Okay, what is remaining is, of course, to see that Rj is equal to 1, Daj has full dimension, it's actually winning, and this part. Okay. So again, we won't do any work. We'll do as much work as Davenport-Schmidt. Okay. So Daj is winning. So there's a paper of Estal, Shu, and Christensen, which again gives a winning strategy for Daj. So the strategy, if I understand correctly, is similar to the strategy Schmidt gave, but I think they prove a little more. They prove that Daj intersected with fractals also has, some fractals also has full dimension, something like that. But in any case, all we need is that Daj has full dimension, and they do it for a whole bunch of rings of integers. Okay. Okay, so again, for free, we have Daj is winning. Okay.
Whole story could be for other rings.
Other what?
Other rings other than ZJ.
There's something.
There are some substitutes.
I will. Something will change. I'll do Gaussian next, and something will change. Yeah. That's the inspiration. Okay. Okay. Yeah. Okay. Yeah. Dani's correspondence. So we also have Dani on our side. So yeah, proving that Daj has like full dimension can also be done by just ideas like games played on like homogeneous spaces or like just. Okay. The point I'm trying to make is that there's this correspondence of Dani, which is that number is badly approximable if and only if the forward orbit of lambda alpha j is bounded, or this set is precompact in Xj. So Dani's proof of this, again, it's not hard, but what we did before, that change of variables, is inspired exactly by what he did. It's very similar. It's just, again, you have, yeah, I won't say anything more. Okay, so we have these two equivalences of the badly-approximable property and the Dirichlet-improvable property in terms of orbit in this homogeneous space. Okay. So two remaining things. Why is Rj 1 and why is dA contained in di? Okay, so remember, Rj was the critical radius defined as the Minkowski constant for this convex body, and Lj was the set of critical lattices. Okay, so sphere packing, I guess, has been in the news. So if you if you think about it, answering these two questions, like what is Rj and what is this set, is exactly answering this question. So in the space of all Eisenstein lattices, not just determinant 1, which lattices give the densest packing of C2 by this domains? Again, this is disk times disk. How do I pack space most efficiently by Eisenstein lattices with this domain? And once you find that set, so all of them will have the same absolute value of determinant. So you can scale and bring it into this space. What does that look like? So figuring out the packing density corresponds to figuring this thing out, figuring out exactly which lattices pack it the best corresponds to figuring what this is. Okay, and Minkowski, there's like an obscure theorem of Minkowski where he completely solves this problem. So his motivation was not packing, but it was just to give an analogous linear forms theorem. I mean, that's what he calls it, linear forms theorem for the Eisenstein integers. So again, you need to do some change of variables, but this is what the critical locus is. And it's in his book, Diophantine approximation. Now, let's do a sanity check, maybe, to see what this actually is saying.
So Minkowski has a book called
Diophantine
approximation.
Yes.
And it's in German.
Yes.
Did you actually look at it?
Yes.
How is it?
How does it prove
what's the
this?
experience? No, not about, I'm just curious.
I can tell you how he proved it. Yeah.
I'm curious to know what goes into this. Wrote it when?
1907. I think that was before Geometry de Zahlen, or I don't know. So maybe around the same time.
And is it interesting? Did you get inspired by it?
I was looking for something else and then I saw this. I got lucky. Oh no, I use Google Translate a lot. I don't know German. What? No.
Did you get a feeling that so whenever I kind of looked at the text of people doing Diophantine approximation,
Yeah.
like old versions,
Yeah.
I have this constant feeling that they completely do homogeneous dynamics in their head, but they are writing it in a disguised form, kind of burying all the arguments and all the intuition behind the equations. And I was wondering if you had the same feeling.
So at least this chapter is a lot more about optimization. It's, yeah. I mean,
so no dynamics, just like finding extreme lattices.
Yeah, exactly. Finding extreme lattices. At least this chapter. I'm not sure what goes into the other ones. But you're right. I felt that way about like reading Davenport-Schmidt. They're doing homogeneous. Yeah, of course, yeah.
They're trying
Too hard.
not to understand.
Okay, so I mean, okay, if you unpack all this, what this is saying is that if you fix the radius to be 1/2, then the standard Eisenstein lattice gives the densest packing of this domain. And you can check the density is pi squared over 12. But this matches with what you see in 2 dimensions. So if you take the half supernorm ball in the complex norm, it looks like a disk. The Eisenstein lattice packs this in the best way. amongst all lattices and in general, not even amongst all lattices. So yeah, the density is square.
And this just follows from the two-dimensional case.
No. Okay. So is there anything else? Okay, I can tell you. Yeah. So I mean, it's not an easy theorem to prove. This is something that goes into it. What you can reduce the problem to is saying you have two C-independent vectors on the boundary, and then you have to minimize the determinant subject to the condition that the lattice generated intersects the convex body trivially. So you have a finite number of conditions which partition this thing into some domains, and you have to minimize the determinant. So it's not pleasant, but he did it.
It has a calculus flavor?
Not even so much. I mean, the main thing is just figuring out these domains. It just breaks into cases. He just had somehow had the patience and insight to.
What is this drawing that you are showing?
So okay, I can explain the drawing. So it's exactly you see that this is equivalent to solving the following problem. You have your domain in C cross C, and you want to find a lattice of minimal co-volume which intersects this ball trivially. That's the problem. So very easily you can see that you need two independent vectors, one here and one here.
So this relates to the first question that you asked. Are you looking at? You need this lattice to be a ZJ model.
Yes.
So are you completely free?
I mean, the conditions that you get depend on DJ. I mean, when I say I want the generated lattice. When I say generated, yeah, that's where ZJ is coming in. Yeah, yes, that it does come. Yeah. So yeah, what I'm basically showing you is the projection of one of these or of both of these things to one coordinate, because yeah, the problem is invariant under multiplying by e to the IT, I guess, e to the minus IT or even more. So you can assume that you have two vectors of the form 1 sigma rho 1 or something like that. And then what I'm showing you is the projection to one coordinate. So it's trying to optimize two values in something like that. Okay. Now the whole point of this is that these lattices have an incredibly striking property. They're divergent. Every single lattice here is divergent either in the forward direction or the backward direction. So remember, divergent in the space of lattices means having a very small vector. And when I say divergent, I mean divergent under the diagonal flow GS. So I hope that's clear. Like, for example, if you take something in the first lattice, you always have e to the IT, this vector. And then when you look at e to the s, 0, 0, e to the minus s, as s goes to minus infinity, this vector is going to 0. It's a huge property of this. Like,
but it's not. It's very reminiscent to what happens in dimension 2. And
yeah. Davenport and Schmidt implicitly use the same property in the real critical locus. They're all divergent lattices. Okay.
Saying more, you're saying that.
I mean, they're trivially. What?
You're saying more than they're all divergent, right? Or divergent are they?
Are what?
It's the same set, right? I mean, this is what you're all
the set of critical lattices is exactly the set of lattices that are generated by two such vectors, but by
this is
set of these lattices.
Yeah. I'm saying more, but the divergence property, or it turns out you can rewrite Davenport-Schmidt's argument with the help of Dani in one line. So why is BA contained in BI? Okay, so remember we have something is in BA, that means the forward orbit is precompact. something is in DI if and only if it avoids the critical locus. So suppose something in DA is not in DI. That means it accumulates on the critical locus. So if we look at this,
Anything in the critical locus has an unbounded.
yeah, so it'll pull it out. Yeah, so it can't happen. I mean, so we don't need divergent, just unbounded will do. So that's, yeah, BA is contained in DI. So yeah, we did as much work as Davenport-Schmidt. Okay. Okay. So yeah, that's the end of the Eisenstein-Dirichlet theorem.
And what would change if you would change the ring of integer?
Yeah.
So,
Huh?
will something change if you replace J by something else?
So let's do the Gaussian integers. This you might, yeah, okay. So now everything is co-volume 1. Yeah. Okay. So Gaussian integers is the standard lattice in C, generated by 1i. This is the Dirichlet theorem. You don't have 1 anymore, but you have this awful constant. This is the optimal constant. Again, you can just
Wonder is a footnote?
where? No, it's an inverse. It's an inverse. Yeah. I'm sorry, I forgot to figure out what this exactly is. I think it's 1.1, something like that. I'm not sure. I need to look at it. But again, you can define the set of Dirichlet-improvable numbers. You can show that it has measure 0. And again, you can show that it has full Hausdorff dimension, but not by this BA contained in BI argument. And the reason is, well, maybe you can just guess from here. This lattice does not pack the disk efficiently. So Zi cross Zi is not going to pack the soup norm ball efficiently. You need to twist it a little. And again, Minkowski solved this. So again, he says in the same book, because he gives a linear forms theorem for Gaussian integers as well. And this is what the critical locus looks like. Yeah, so
You guys do not have unbounded.
work in progress. I don't know. I'm not sure. And yeah, yeah, just the point I'm trying to make is that the connection between DA and DI is lost. You still have the same theorem, but again, you need to use a different kind of winning argument due to Arnguan and Kleinbach, which uses the differential geometry of how this thing sits in the space of lattices. But it begs the question, when exactly is that contained in Dirichlet? So in other words, when can you construct a pre-compact orbit with a prescribed limit point? This Davenport-Schmidt, Dani show that one obvious obstruction is the orbit of lambda itself being unbounded. If that happens, you cannot construct bounded orbits with this prescribed limit point. So I'm asking for the converse. Given a lattice with pre-compact R orbit, can you construct a big number of bounded orbits which accumulate on lambda? So maybe I should mention what limit point means. Maybe I've defined it. Yeah, so lambda 2 is a limit point of lambda 1 if in the geodesic flow you have a sequence of time going to infinity such that dt and lambda 1 converges to lambda 2. Okay, I have 1 minute left, and I'm going to show you a theorem. So in SL2R mod SL2Z, you can. So given this limit point, pre-compact orbit, you can construct a full Hausdorff dimension set on the horocycle and hence a full Hausdorff dimension in the homogeneous space of bounded orbits which accumulate on lambda 0. Okay. Yeah, that's it.
And this is using games? Yeah?
No, this is not. These things cannot be a winning set. But yeah, it's not. These things are never a winning set, but it's using symbolic dynamics. Okay. Okay. Questions? Thank you.
So, Minkowski, do you have some general statement about
Just these two things. Just these two things. It's not at all easy to prove. Yeah.
When you say the end, it's okay. This identity. I'm curious that you said that done by symbolic dynamics.
We spoke about this transversal, right?
I was just curious about what you said at the very end that we're using symbolic dynamics to.
Yeah, so we use a transversal for SL2R mod SL2Z.
Okay.
Yeah, I was asking you about transversals, right? Yeah.
So do you think that if I would consider all, I want to replace ZJ by other ways of integers and kind of split them into those for which the critical have bounded orbits and those for which
it has unbounded. Or I mean, you need to split it into cases where every single one is unbounded, or there exists at least one bounded. Yeah.
do you think you could
Characterize.
even without understanding the critical lattices, which you say is very hard, I guess. Wondering if that some property related to the algebraicity of the number is somehow manifested in a way that shows boundedness / unbounded.
Yeah, I mean, if it really, we would need more examples. I feel like, yeah. I mean, I can't say anything at this point. It would. Yeah, I mean that would be very desirable. But yeah, even like norm balls in the real case, if you have cylindrical norms, it's like even not known then whether you have.
Yeah.
It's very hard. Yes. Okay.
Not more.
I was going to this was going to meet the GDRT. We have so many audio